Bismillahirrahmanirrahim. Assalamu alaikum. Today I have selected a topic of chapter number 8, Electrochemistry. It is part 2. And in this part, we will discuss Faraday's law of electrolysis, Faraday's first law of electrolysis, electrochemical equivalent with example, Faraday's second law of electrolysis, relationship between electrochemical equivalent and electrovalent and equivalent mass, unit of current and electric charge, and uses of electrolyte with example. Faraday's law of electrolysis. Michael Faraday in 1833 discovered the quantitative laws governing the process of electrolysis, which are known as Faraday's laws of electrolysis. There are two laws of electrolysis put forward by Faraday. Faraday's first law of electrolysis. It states that the amount of any substance deposited or liberated at an electrode during electrolysis is directly proportional to the quantity of current passed through the electrolyte. W is the amount of substance and A is the current and T is time. W is directly proportional to the current passed through the electrolyte. If we replace the sign of proportionality, we apply a constant and Z is constant. Where Z is a constant known as electrochemical equivalent of the substance. If 1 ampere of current is passed for 1 second, then W is equal to Z. This means when 1 ampere of current is passed for 1 second, then the weight or amount of the substance deposited or liberated is exactly equal its electrochemical equivalent. The current in ampere multiplied by time in second is known as coulomb, which is the electric charge. Ampere multiplied by time is equal to coulomb. Now, electrochemical equivalent. Electrochemical equivalent of a substance may be defined as the weight or amount of the substance deposited or liberated when 1 coulomb of electric charge is passed through an electrolyte. It is denoted by Z, and in SI unit it is expressed in kilogram per coulomb. Each element has its own electrochemical equivalent. Now, Faraday's second law of electrolysis. It states that the masses of different substances deposited or liberated when same quantity of current is passed through different electrolytes connected in series are proportional to their electrochemical equivalent chemical equivalent masses. Consideration. Consider three different electrolytes: silver nitrate, copper sulfate, and aluminum nitrate solutions. They are connected in series. Same quantity of current is passed through them, then the masses of silver, copper, and aluminum deposited on their respective electrodes would directly proportional to their equivalent masses. According to Faraday, if exactly 96500 coulombs of electric charge is passed, then the mass of silver deposited would be equal to 108 gram. That of copper is 31.75 gram, because the atomic mass of silver is 108 and the valency of silver is 1. So 108 is divided by 1 because silver carry 1 positive charge, while the atomic mass of copper is 63.5, but the valency of copper is 2 and copper carries positive 2 charge. So the equivalent mass of copper is equal to 63.5 divided by 2, which is equal to 31.75 gram, and aluminium is 9 gram, because the atomic mass of aluminium is 27 gram, but aluminium carries positive 3 charge. So its atomic mass is divided by 3, which is equal to 9, which are their equivalent masses respectively. Now equivalent mass of an element is equal to atomic mass of the element divided by valency of the element. The current of 96,500 coulombs is called as 1 Faraday. Charge after the name of Faraday. Thus Faraday is defined as the quantity charge which deposits or liberates exactly 1 gram equivalent of a substance. Now, the relationship between electrochemical equivalent and equivalent mass. Since 96,500 coulomb is equal to 1 Faraday, electric charge is required to liberate 1 gram equivalent mass of a substance. So it is clear that the gram equivalent mass of a substance is 96,500 times greater than its electrochemical equivalent. Gram equivalent mass is equal to 96,500 multiplied by electrochemical equivalent, that is Z. In other words, if E is the gram equivalent mass and Z is the electrochemical equivalent, then we can write it as E is equal to 96,500 multiplied by Z, or E equal to F multiplied by Z. Now the unit of current and electric charge. The unit of current is ampere. It is the basic unit of current in the international system or SI system. It may be defined as the current when passed through a circuit for 1 second can liberate 0.001118 gram or 1.118 into 10 raised to the power minus 6 kilogram of silver from silver nitrate solution. Now the unit of electric charge is coulomb. It is the SI unit of electric charge and is defined as the quantity of charge when 1 ampere of current is passed for 1 second. So C is equal to ampere multiplied by time, or 1 coulomb is equal to 1 ampere into 1 second. A coulomb is equivalent to ampere multiplied by seconds. For example, a current of 0.5 ampere following for 80 seconds gives a charge 0.5 multiplied by 80 is equal to 40 coulombs. Now the example, when an aqueous solution of copper sulfate is electrolyzed, copper metal is deposited at cathode. Copper 2 positive, it gains 2 electrons, and copper solid is deposited at cathode. If a constant current was passed for 5 hours and 404 milligram of copper was deposited, calculate the current passed through copper sulfate. Now the data, amount of copper deposited is equal to 404 milligram. When 404 milligram is divided by 1000, it is equal to 0.404 gram. Gain of 2 electron means 2 Faraday electric charge. Atomic mass of copper is 63.5. According to cathode reaction, 63.5 gram of copper is deposited by 2 Faraday electric charge. So 0.404 gram of copper is deposited by 2 divided by 63.5 multiplied by 0.404, which is equal to 0.0127 Faraday. One Faraday is equal to 96,500 coulomb. So 0.0127 Faraday is equal to 0.0127 into 96,500, which is equal to 1225.6 coulomb. Because the coulomb is equal to ampere multiplied by time in second. So time is equal to 5 hours. So ampere is equal to coulomb divided by time. We obtain 1225.6 coulomb divided by 5 into 60 because 1 hour contains 60 minutes and 1 minute contains 60 seconds. After calculation, we obtain 0.0680, which is, it can also be written as 6.80 into 10 raised to the power minus 2. And the unit of current is ampere. Now the example. For example, impure copper blister is purified by the process of electrolysis. In this process, the impure copper, that is blister copper, is made as anode in the electrolytic cell. Cathode is a thin plate or sheet of pure copper metal, and the two electrodes are dipped in the electrolytic solution of copper sulfate containing few drops of sulfuric acid. The two electrodes are connected to a battery, that is source of electricity. When an electric current is passed through the electrolytic solution, the copper anode dissolves in the solution as copper 2 ions, which move towards cathode and gain electrons to get neutralized, depositing pure copper metal over cathode plate. Most of the impurities of anode fall to the bottom of the cell called as anode mud. Copper thus deposited at cathode is 99.99% pure. In this way, copper anode, that is blister copper, dissolves completely to form pure copper at cathode. This process of electrolysis is similar to electroplating. Thank you very much. Allah Hafiz.